example 7, ¿no? My paper at least is 7. I don't know si it's the continuation perfectly. 32 raised to x plus 2. Remember, this is the exponent. That is the reason I put a small in the top part. Equals 16 raised to the 2 minus 6. Okay. Entonces, what is the key idea? What is the key idea for solving this kind of equation, que es called exponential equation, is you manipulate both sides in order to express it using a common base, And when you can get that, express both sides using one common base, magically happen, it's magic, mathematical magic, que you convert this equation, que es exponential equation, to another super easy linear equation. Not always is linear, but frequently is linear equation. And you solve a linear equation like we are doing in MIT 1033, intermediate algebra. Okay, so this is a key idea, to find the common base. What do you suppose is the common base in this example? What do you suppose is the common base? 32 and 16 is the base of these two exponential functions, no? But I need to manipulate, I don't know, see. Es tú, very well, Rosalinda. Rosalinda say que es tú. How do you know que es tú, guy? Because 32 is 2 to the 5th power. So 2 times 2 times 2 times 2 times 2, 5 times is 32. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. Perfect. And 16 is 2 to the 4th power. Okay, so you replace it, not 32 anymore. No. It's 2 to the 5th power raised to the x plus 2. And 16, no 16 anymore, it's 2 to the 4th power raised to the 2 minus x. Huh? So you're using the classical rule of the exponent, is, suppose when you have one base, I don't know, let me call A, raised to the x and raised to the y, is equivalent to say x to the x times y, multiplication. You multiply different level. You have 2 or 3 or 4, multiply, it's multiplication. So it's basically it's 2 and 5, multiply everything, x plus 2. This is the countable way to express these ideas using binaries, grouping symbol. Likewise, in the right hand side, we have 2, 4 times 2 minus 6. Okay, so in this moment, we have two exponential functions, but the base is the common base, que es 2. Therefore, if we have two exponential functions and the base is the same, it's because the exponent is the same. So you convert magically this exponential equation and one equation like that, 5 parentheses x plus 2 equals 4 parentheses 2 minus x. But however, no, you actually remove the base mentally. The justification, this idea is because the exponential function is a one-to-one function. You remember in the last class, we are doing quickly, of course, the exponential graph look like that. Well, we have two exponential growth and exponential decay, but suppose we focus in exponential growth. Well, in this case, growth because the base is greater than 1. And so you apply the famous horizontal line test. Do you remember it's the test that we use to determine if one function is one-to-one function or no, and crossing only one point? Therefore, that means that one value of the x corresponds to only one value of the y, not two. Therefore, this is the reason that we can eliminate. This is the y1, this is the y2 of the two different exponential functions, but the base is the same, so the x is the same. So the rest is piece okay for us. You apply this tree with the property, 5x plus 10. Apply distributive property again. 8 minus 4x. You try to solve for x. So 5x plus 4x. I move 4 to the right-hand side positive. A minus 10. It's a 9x, and this is minus 2. Finally, divided by 9. So my final answer is x equal minus 2 over 9. Is, wait, by the way, well, no always, but frequently happen that we have only one solution, and you don't need to checking. No checking, no check. If you want to check it, you can, but no mandatory checking. No checking in the exponential equation. Because exponential equations are nice. What is the reason it's nice? Because the domain of the exponential equation is all real number. You see another equation that we studied in this chapter. It's a little bit picky, and you need to check it. But the exponential, no, never. Because the domain is all real number. There are no restrictions. Should be positive, should be negative, should be irrational. Any real number is a potential solution for this. Any question, guy? Do you understand very well this? This is easy. I promise in the test, you see two examples of the exponential function similar to this. Because we have two exponential. We have one easy, like that, and one hard. Okay, so far we don't study the hard exponential. Okay? But no hard for the moment. Only easy, focusing on the easy. One more example. Easy. Example 8. You have a question or no? Come on. I want to see your face. Yes, no. Do you understand very well? Yes or no? We have time. Slow down. It's important that you ask me any question. No. Yes. What means yes? Can you have a question or you understand? I suppose you understand, right? Okay, clear. I love you, this answer, clear. Okay, I let me see if I record. Yeah, I record. Somebody do a favor to record. Okay, guys, let me go to another example. I call example 8. Example 8. Okay, example 8 now. Example 8. Example 8 is cubic root of 5 raised to the minus x. Wow, what the hell is that? It's a cubic root and also negative exponent. Okay. Another parenthesis, 1/5 raised to the x plus 2. Wow. Okay. So I realize a little bit. Okay, it's possible. Find the common base. Okay, I need to find the common base. And also try to express both sides using the common base. No? What is the common base, guys? What is the common base? Help me. Help me, please. X, no. X, no. No X. Common base. No idea? Okay, actually, what is the base of the left-hand side? Well, the base is the left-hand side. The base is cubic root 5. And the right-hand side, the base of the right-hand side is 1/5. Look like there's something in common or no? What is the something you see in common? 5. So my common base is obviously 5. Okay. But I try to use my common sense in order to express it. Let me see here. Cubic root of 5. Bueno, cubic root of 5. I need to remember que Rayleigh notation is possible to express it using fraction notation. Okay, 1/3. Why 1/3, professor? Because look, this the top part of the fraction is this exponent. Okay, by the way, it's invisible. It's 5 to the 1 power. Now, si it's 25, no. But it's just 5. So 1, this one is this one, and this 3 is this 3, gets the index of the root. Index. Okay, so I express the left-hand side using the common base, get 5. Okay. And 1/5, 1/5 is easy. 1/5 is 5 to the negative 1, because negative 1 is reciprocal. And that's it. So you replace this expression and this expression here. Instead of cubic root, no cubic root anymore. It's 1/3 raised to the minus x is equal 5 to the negative 1 exponent raised to the x plus 2. Okay? And one more time, we're using the property of the exponent, different level of the exponent multiplication. So 5 multiplication by 1/3, well, it's minus x, no? The negative and positive and negative, right? And the right hand side is exactly the same. Negative 1 times this is negative 1, x plus 2. Well, I omit the negative 1 because, you know, sometimes it's invisible. Negative 1, no? This is like algebra style. Okay. Now in this case, if the base, you have two exponential, the base is the same as 5, therefore the conclusion, then the exponent is the same. So minus 1/3 x is equal minus x plus 2. Okay, too many negative. I don't like that. You multiply the entire equation by negative 1. Because I want to remove x 1/3 x is equal x plus 2 without negative 1, no? Entonces I don't like, never I like the fraction. Keep the fraction. Multiplication, the entire equation by 3 is our least common denominator. Entonces x is equal 3x plus 6. Okay, 3 times 1/3 is obviously 1, invisible. 3 times x is 3x, and 3 times 2 is 6. Okay, the rest is solved for x. I move equals 6. Subtraction, combine, 2x equals 6, divided by negative 2 both sides. Therefore, x is equal minus 3. It's the final answer. Let me check in my paper. Yeah, it's the final answer. Okay? Okay, entonces, don't forget, okay, I can complicate a little bit your life using radical, using reciprocal, using negative exponent. You need to be aware for the different situations. Okay? I promise in your moment, we go over again to this problem, no? We practice more in the review packet. We have a lot of typical example you see in the test. Entonces, any questions so far, guys? No problem. Everyone follow me today. Super good. Yeah. Okay. Let me say something. This class becoming my favorite class. At the beginning, no. At the beginning, no. But little by little, I feel you are learning very well. So yeah, your behavior is different. The participation on the ask equation, you get the correct answer. Another class I have, oof. No, it's not compliment. It's real fact. It's real. About you, Rosalinda, Flora, Jordan. No. Okay. Okay. I encourage you, the student can need to take next semester. Yeah. Actually, Launa, we are the best in Miami-Dade College. The student can need to take pre-calculus. I will be teaching pre-calculus in the spring. I suppose it's the same online because the pandemic continues, no? Until April, maybe it's vaccinate. But I teach again this class called algebra. I teach any semester. I will be teaching pre-calculus alone, so MAC1140. Yeah, I teach in the combination both pre-calculus and and algebra, que es together, que es integrated. This is a new for me, pero ese es, I feel good. It's 5 credit class, que es the combination. No, but you don't need to take because you pass algebra, no? Okay, guys, I have a challenge for you now. Suppose this we are exponential equation. 2 to the x equal 3. Compare with this versus 2 to the x equal 4. Oh, this is a piece of cake. Because I know que 4 is 2 to the second power, same exponential, same base. Therefore, the conclusion is x equal 2. But in this case, impossible. It's impossible because we cannot express 3 like a power of 2. But we have solution or no solution? No solution or yes? Yes, we have solution. The answer is yes, we have. But the problem is for solving this, you need to understand a new concept that you never see before, que es logarithmic function. Okay, let me put the title for that part for solving this equation. Remember, I keep this equation. Maybe today we're solving this, but we need to study one new theoretical part for solving it. Well, the new theoretical part is a logarithmic function. Okay, logarithmic function. Okay, logarithmic function. Okay, I promise que es the last function that we study in algebra. We study natural logarithmic. No, but not necessarily natural. I study in general logarithm, but we go focus to the natural. Yeah, you are right, Jordan. You are right, but no, now. Slow down. Slow down. Okay. In your moment, we study natural. Yes, absolutely. Okay, entonces, what is the idea for the logarithmic function? Well, logarithmic function, the definition is logarithmic function is the inverse function of exponential. You remember that the first topic that we studied in this chapter was inverse, no? Function. 1 to 1, inverse function, and suppose that the inverse function for the x squared is square root, and the inverse function for the multiplication by 2 is division by 2, no? This is the idea. Inverse function is in opposite direction, no? But logarithm is in opposite direction to the exponential. So let me try to explain this idea carefully. Let me recall exponential again. Recall exponential. Exponential is y equal a to the x. And remember, a is the base. And the base is a real number, but not all real number. Only positive, real number. But a is always positive, never negative. It's mistake, totally wrong, base negative. And no 0, and no 1, because it's a trivial example. It's a trivial, stupid, trivial. And this is the restriction for the base. No negative. Positive. This is the definition of I recall exponential. Now this is the crucial moment to go to the logarithmic. Is the new one. I say get the inverse. And remember, to find the inverse, the procedure that we study is interchange x and y. Something like that. I suppose you remember this idea. Interchange. So says you put x here, you put y. Voila! And this is the inverse. But as always happens, is the inverse and implicit form. And implicit never is nice. It's ugly. It's no countable. However, I like explicit, it's clear. And explicit is when you solve for y. So when you solve for y, the manipulation is, look, you declare the name of the function. Remember, the name of the function, basically, we're using 2 letters or 3 letters, log. So in order to express in explicit form, you put log, and your specification here in one corner down, one number is the base, you specify the base, and inside the parenthesis is like a function notation, no, like a y equal f of x. But in this case, the name of the function is no f, it's log, and your specification the base. It's important, the specification. And this is the inverse function in explicit form. Okay, so this in explicit form is the logarithmic. Okay, I suppose that you don't understand anything. No, because this is the definition, well, okay, es formal, blah, 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 pero no clear, unclear. So I want to explain the interpretation of this. It's the most important, interpretation. Interpretation of the logarithmic function, no? What is the goal? What is the thing that you're looking for? Well, okay. So I come back again, the exponential statement. Suppose exponential statement, and clear, I studied last class. Exponential statement. And here, logarithmic statement. I want to compare logarithmic statement. Okay, logarithmic statement, exponential statement, and let's see some example, elementary example, no big deal to understand the interpretation. Or of the exponential statement, you write something like that: 2 to the 5th power is equal to 32. Everyone understands very well this, because as you multiply 2 5 times, 2 times 2 times 2, and you get 32. But this is equivalent in the logarithmic statement. You put log like that, log, get the name of the function, logarithmic, and your specification, the base, the base is 2. Look at that, the base is 2, and the exponential associated with this. Then inside the parenthesis, you put 32, is this answer, and the answer is 5. Wow, what the hell is that? What is the interpretation of the logarithmic? Well, the logarithmic give me what exponent is necessary to raise 2 in order to get 32. It's completely backward, okay? You need to find the answer que offer the logarithmic statement is the exponent, is this number. Give me the number in which you need to raise the base, que es 2 in this case, in order to get that number, que es the number que you suppose que is the domain of the logarithmic function, que is this value, x. Okay, partial clear. I at least in this moment I realize that the answer for the logarithm is the exponent. Okay. Let me try another example. Is 3 to the 4th power equal 81? It's clear because 3 times 3 times 3, 3 times 3 times 3 times 3. Well, 3 times 3 I know is 9. 3 times 3 is 9 again, and 9 times 9 is 81. Perfect. How you express this statement, exponential statement, like a logarithm? Logarithm, log again. The base is 3. It's obvious because the base is 3. Of the 81 should be 4. Okay, don't forget this example, because in one moment, maybe next time, we compute this using the calculator. Okay, now today is the day of the definition. Today is the day to understand the logarithmic function. But I promise, okay, not today. Next time, we're using the calculator. So I want to teach how using the calculator you get the same answer. In this case, the same answer is obvious because I select elementary example, but not always is obvious. And now you need to use the calculator. Okay? Okay, entonces en general, I understand now that in general, In general, we have two different words separated by this line. The exponential word. The exponential word, we have base raised to the something. I call exponent, no? Exponent. And give me one number. I want to call result. I don't know why I want to call result. Result of the exponential. And when you translate this to the logarithm statement, you put the magic new word log. You put a small number here to indicate the base. And you put here result. And the answer is the exponent. Okay? This is the key idea in the exponential. I repeat again the idea. Logarithm always give me the exponent in which you need to raise the base in order to get the result. Okay, okay. I suppose that you are not clear. So let's practice a little bit, and you help me. For example, let's do it first. Several logarithms by hand, no calculator, no, today no calculator, today intuition, because I need to understand very well logarithmic function. Entonces, suppose the base que es easy to understand is the base 10. It's the base 10, it's easy without calculator because base 10, for example, base 10 of the 100. What do you think about this? What is the logarithm of base 10 of the 100? Remember the idea. Logarithm give me exponent in which I need to raise the base. Is what? Es 2. Very well. Very, very well. Es 2. Es 2, es 2, es 2, es 2. Es 2. Es 2 because intuition, no calculator, is 10 to the second power is 100. Okay. Another way, que I strongly recommend, look, is you have no idea. I am in the jungle without calculator. No, I promise, if we computed this in 1 second, no? I put in the calculator, pa, 2, the answer is 2. But no, today is the day to understand the idea. Suppose que I want to find this, I have no idea, I'm lost, totally lost, it's complicated for me. Then I convert this statement, que es logarithm statement, to exponential, no? Let's do it pero in opposite direction, in this direction, no? Entonces, the base is 10. I copy this 10, que es small, I copy big. The exponent is, I have no idea. I am totally lost. And the answer is 100. Oh, but I know that 100 is 10 to the second power, no? Because it's 10 times 10. Therefore, in this case, we have two exponentials with the same base, and you convert to the linear equation, x equal to. Final answer. Don't hesitate, guys. Don't hesitate. We can use the calculator in your moment I teach how. Or you convert the logarithm statement to exponential and you definitely compute the exponent. Pero no, I want to complicate more your life. Logarithm base 10, que es easy to understand, of 1000. Come on, another participation. No, Jordan, another participation. What is the answer of this? Come on. Answer me. Logarithm 3. Es obvio que es 3. Everyone saw que es 3. Oh, it's easy, professor. I understand. Because you count how many zeros we have? 1, 2, 0, 3, 0. Wow. When it's 10. I select 10 because it's easy to understand. And what about 1 million? 1, 2, 3, 4, 5, and 6. What is the answer? Logarithm base 10 of 1 million. 6. Very well. I want to complicate your life. I put it easy way first, and you are happy now. But I try to complicate your life. Logarithm base 10 of 10. What do you think about it? Tell me. I need help. What is that? 1. Very well. How do you know, Jonathan? Bueno, Jonathan dice, bueno, profesor, because 10 have Florentino. Carlos Florentino dice, 1. Explaining. What do you think que es 1? Bueno, profesor, porque yo explain que 100 to 0, 1000 is 30, 1,000,000 is 60, and 10 have 10. Okay, perfect. Perfect, but okay, more scientific way to see that, you put x, you convert to exponential, the base is 10 to the x power, and 10 is just 10 to the 1. Therefore, the equation is x equal 1, because the exponent is the same. Look, two exponential, same base, is because the exponent is the same. Okay, I understand very well. Now, a challenge now. Point 1. What do you think about point 1? Come on, you can do that. It's no big deal. This is acceptable. A little bit weird, I understand, but it's acceptable.
-1.
-1, very well. -1. -1 is the answer. Okay. Why? I don't understand very well. Why -1? Because, again, I put x because I have no idea. I convert to exponential. 10 to the x is equal 0.1. Pero 0.1 I know en fraction is 1/10. And 1/10 is reciprocal, is 10 to the -1. Remember, raised to the -1 is reciprocal, flip it. Therefore, we have in that moment two exponential, and the exponent is the same, x equal negative. Exactly, she said. Who said that? Flora. Guy, I have Flora. No, Flora no, it's Flora no. Who answered this question? No, there's only two no. No me, no Flora. But Flora always answered good question. Okay, who helped me with the using the same routine? 0.01. Wow. And logarithm base 10 of 0.001. Come on, help me, guy, please.
-2 and -3.
-2 and -3. -2 and -3. No, -10 no. Okay, let me explain. Suppose the first one. Some weird. It's a contra the intuition. Suppose x, and immediately, in order to solve this, I convert the logarithm statement to exponential statement, ¿no? Entonces, 10 to the x is equal to 0.01, and 0.01 is 1/100. If 1/100 is 1/10 squared, because you know 100 here is 10 squared. Look at here. But the reciprocal, entonces 10 to the -2. So in this moment we have two exponential, the same base, therefore x is -2. So using the intuition and the common sense, this is -1, this is -2, this is -3, ¿no? Entonces depende de 1, 2, and 3 decimal place. That's 3 decimal place, -3. 2 decimal place, -2. 1 decimal place, -1. And what about? Logarithm base 10? Push. Wait. Okay. Let me make it zoom. Here. Okay, good. I need to erase the board because the board become slow when I write too much. It's logarithm base 10 of 1. Blanca. It's another class. Okay. Another class. Annoy me. Es 0. It's 0. She said it's 0. Flora, no? Let me see. I have no idea. It's x. When I convert to exponential, it's 10 to the x. equal 1. And you need to know that any number or expression raised to the 0 power is equal 1. Therefore, x is equal to 0 because we have the same base and the exponential x equals 0. Okay, guys, entonces we discover two important properties that we are using every day from today. Logarithm of the any base, I don't care the base, of 1 is 0, always is 0. In this case, A is 10, and you prove que es, pero in general, it's the same, is A to the 0 is equal 1. So when I convert this logarithm statement to exponential statement, no? This is my first property. My second property que I discovered of the logarithm base A of A, that when there are coincidence in between the number, look, in the case que is 10 base, look at that, is this example, no? Que was 1, the answer. Entonces, when the base is the same, o sea, when the argument inside the domain of the function x value is equal to the base, the answer is always 1. Because a to the 1 is. Now you can see, for example, in the several examples we are doing, logarithm base 2 of 2, logarithm base 3 of 3, logarithm base 2 of 1, logarithm base 2, base 3 of 1. This is 1, this is 1, this is 0, and this is 0. Because when it's 1, it's always 0, regardless the base. Que es 3, es 2, es 4, es 20, whatever. And when the base and the number inside the argument is the same, look at that. Property number 2, the answer is always 1. This is completely, at least no intuitive idea when you work in the first time in the logarithm world. It's confusing to this. Any questions so far? I bring 1, 2, 3, and 4 examples. You help me to understand this. 4 more examples. No base 10 anymore. I'm using another base because I want to extend, the idea of this. Suppose the example 1. So we compute without calculator now logarithm base 4 of 64. Question mark. I have no idea. What do you think? Well, I have no idea, actually. S3, Andreina say S3, Andreina, you're right. S3, S3, S3. Because remember, what exponent is necessary to raise 4 in order to get 64? Okay. Suppose you don't see using intuition, no problem. What is the systematic way without calculator? You convert this statement, logarithm statement, to exponential. You put a big 4, this 4, big 4, this big 4 is this small 4, is the base. When you change to exponential, the exponent is exactly what I'm looking for. I have no idea. It's equal to 64. So 64, I know get 4 to the third power, no? Because 4 times 4 is 16, and 16 times 4. You put in the calculator, 4 times 4 times 4 times 4, until you get 64. And see, you never get 64 is because we need to use in the calculator. But in this case, no. Says you convert 64 to the exponent, but it's the same base. So in this moment, we have two exponential with the same base. Therefore, the conclusion is x equal. But always, you can get the answer without a calculator when the example is easy. When the example is complicated, no. Of course, no. The second example is logarithm of base 5 of 1 over 125. Ooh, what the hell is that? I don't understand very well, professor. Help me. No? Not clear? Okay. It's confusing, right? It's confusing because it's reciprocal here, right? But don't worry, reciprocal, you know, okay, it's negative exponent, no? It's reciprocal. Okay, we convert again to exponential. My question is, what is the base? What is that base? And that problem, what's the base in this logarithmic statement?
5.
5. You put the big 5. When you transform it from logarithmic statement to exponential statement, you take this small 5 and you put a big one. What is the exponent? 5 raised to the something. To the, well, to the answer, to the, no.
X.
X, very well. Remember, one more time, I repeat, the answer for the logarithm statement, when you convert to exponential, x the exponent. So in other words, logarithm give me always exponent. Is equal, the rest is the result, I don't know, 125. I know that 125 is 5 to the third power, no? The 5 times 525 times 5, 125. What is reciprocal? Entonces, si es reciprocal, is, bueno, 1 over 5 cubic, no? And reciprocal is 5 to the minus 3. Therefore, in this moment, we have two exponential. Therefore, x is equal to minus 3. Okay? Another example. Suppose logarithm base 3 of 243. Okay. Okay, I have no idea. I'm lost, totally lost. I put the x value. Choo. Yeah, I convert to exponential statement. The base is 3. I put the big 3. This big 3 is a small 3. The exponent is x. It's exactly I'm looking for. F5 is 243. So, basically 3 to the 5th power. Yeah, you are right. 3 to the 5th power is 3 times 3 and 9 times 3 is 27 times 3 is 81. 81 times 3 is 243. Therefore, again, we have two exponential. The base is the same. Therefore, x equals 5. Super. One more example before start to study formally the exponential function. Okay. One more is logarithm base 1/2 of 4 equal x. Wow, professor, I never see before in my life when the base is fraction. I don't understand. Well, okay, the base could be fraction. Remember, the restriction for the base is we have two kinds of exponential. Exponential between 0 and 1 is decay. An exponential base greater than 1 is growth. The restriction is only the base, no negative. No negative. So less than 0, impossible. No. And the base 0, no. And the base 1, no. The rest is okay. Okay, look. In the real line, this infinity positive, this infinity negative. 0, no. 1, no. Negative, no. So the part is no, I put in blue color. No. But in green color, yes. Wow. What happened with the green? Yeah. Green color, yes. And green color, yes. And we have two intervals when the base is bigger than 1, in this case. And when the base is in between 0 and 1. Of course, don't touch 0 and don't touch. Okay? So the definition is okay. The base is totally legal to be 1/2 because 1/2 is here. 1/2. 1/3 is possible. 1/5 is possible. 2/5 is possible. Okay? Entonces, I have no idea how you solving that. What is the answer? -2, Jordan. Jordan said get -2. Okay, but I want to prove Jordan. Maybe Jordan using intuition.
Yeah.
Okay. Intuition is good.
Can I say something?
Okay.
Just a quick
Maybe you are doing using intuition or you are doing algebraically.
No, I'm actually, I guess I'm oversimplifying it. When I know that it's a fraction, I know that the exponent is going to be negative.
Eso bueno.
This
is good. Okay, one good conclusion. When the base is a number bigger than 1, like a 5, like a 3, for example, example 1, example 2, example 3, and the number inside the argument is also greater than 1, like a 64, 243. So we expect positive solution. Look at that. Like that or like that. Like that or like that. Let me repeat again the idea. When the base is greater than 1 and the number inside the argument is also greater than 1, we expect positive solution, positive logarithmic. However, when the base is greater than 1, but the number inside is less than 1, we expect negative solution. Okay, it's correct. No, it's correct, but it's negative number, right? Thus, in this case, it's expecting, okay, when the base is a fraction and the number is no fraction, it's a whole number, okay? Thus, we expect negative value. Good, very good. Suppose I am using the algebraic idea because I am not sure that the answer is negative 2. Jordan said it's negative 2. Let me confirm if it's okay or no. The base is 1/2. Okay, let me write here. Again, logarithm base 1/2 of 4 is x. Okay, I don't have idea. You convert to the exponential statement. 1/2 raised to the x is equal to 4. And so in this moment we have exponential equation. And what is my common base? I suppose that my common base is 2, no? Because 1/2, okay, 1/2 is 2 to the minus 1 raised to the x power, and 4 is 2 to the second power. And you apply multiplication of the exponent, so 2 to the minus x is equal to the second power, and you have two exponential, and the base is the same. It's because negative x is equal to, in conclusion, x is equal to minus. End the story. Now we are the best in Miami-Dade College. Without a calculator, of course, I select elementary example. It's possible. However, the typical problem you see in the real life is not like that. So we need to use a calculator. Okay. Don't worry, be happy. Let's go directly to the formal definition of the logarithm function, and we study their property, is as usually we are doing anytime we study new function, determine domain, determine the range, determine the intersecting y in a set, x in a set, and maybe for example, if you have a horizontal ascent or vertical ascent, I have no idea, or y in a set, x in a set. This is a typical characteristic of the function when you study. I want to propose you switching to Desmos, because in Desmos I prepare one example of this. Look. Let me switch into Desmos, switching, Desmos. There you go. Desmos. Suppose I have the classical exponential function. Again, look, exponential function. Boom. In this example, that was example 1, is the base 2, is the base we are using always to explain this because it's easy to understand. No? This is an exponential function that we studied last class. However, I want to do the graphic of the logarithmic, is the inverse function of this. But it's super easy because the professor explained me that when you are doing the graph of the inverse function, the graph of the inverse function is, what the hell? Okay, is symmetric. Okay, this is the exponential. Let me change the color. Exponential, no blue. Exponential, maybe red color. Boom. A logarithm is blue. The professor explained me when you are doing the graph of the inverse function, the only thing you should do is interchange x and y. Suppose in this point get 2,4 in the exponential, green color. When you switch into logarithm, it's 4,2. Look, it's symmetric. We respect the line y equals x. Can be set the first and third quadrant. Okay. That point is 1,2 and the logarithmic function is 2,1. And this famous point I call universal. I suppose you remember universal point. Universal point in the exponential is 0,1. And also the universal point in the logarithm is 1,0. So any logarithmic function passing through 1,0, regardless the base. In this case, the base is 2, but see the base is 10, it's the same because logarithm 1 always is 0, independent of the base. And negative 1, here negative 1 is 0.5, 1/2. And logarithm 1/2, again, repetition, the same idea. Logarithm of the number less than 1 when the base is greater than 1, so opposite, is negative 1. So this point and this point is symmetric. Look, you interchange x and y. And now logarithmic of 0.5 when the base is 2 is negative 1. And logarithm of 0.25, is 1/4, is negative 2. Okay? Entonces now, si you understand very, very, very well this idea, this graph is clear. Okay. Entonces I try to use my imagination. I try to use my knowledge in college algebra because I want to find. Okay, I try to switch into the whiteboard now. Switching whiteboard. Okay. Okay, whiteboard. Let me erase the whiteboard. Okay, I write too much, and the whiteboard pull is slow to manipulate. So let me try to find. Looking the graph in Desmos, I want to determine domain. Oh, so we are studying property. Okay, of course, properties of logarithmic function. Okay, and the first property we study is domain first. Domain and range. As always, guys, in the test, we write in interval notation. Okay, I switch again to Desmos, and you try to understand. Look in the graph. Remember, we can determine the domain and range. Look in the graph because we project any point on the curve onto the x-axis or the y-axis, depending on if domain or range. Domain is x, range is y. Hello, what the hell I am doing? Look, switching to Desmos. Yes, Desmos. Okay, now here. Remember, the green curve is the exponential. The blue is the logarithmic, is the new one that we study. Looking the blue graph. And if you want to understand what is the domain, you projecting the blue graph onto the x-axis. And you can see, wow, look at that. I projecting here in that branch. I projecting here, down. But what happened in the negative part? In the negative part, yes, the exponential have function, have the curve. Pero logaritmo no. Logaritmo no have. Entonces, logaritmo of the negative number is impossible. It's completely out the domain. Okay? And also, logarithm negative number is completely out the domain, and logarithm 0 is also out the domain, because I suppose you remember that the exponential function have a horizontal asymptote at y0, que es this dotted line. Let me put in. Let me try to see in project mode. Okay. Here you see more clear the asymptote. Now we have a lot of the line, but I don't want to confuse you. For example, let me delete this line, que es the symmetry line. We have two asymptotes, this asymptote and this asymptote. Look, let me remove this asymptote. Let me remove this asymptote. Okay, this asymptote, this one, I put it now, is the horizontal asymptote for the exponential, que es clásica. We studied last time. However, when you find the inverse function, this asymptote, que es horizontal, is transformed to vertical for the logarithm. Look at that. Therefore, logarithmic function approach but never touch. The conclusion is we have a vertical asymptote at x equals 0 for the logarithmic function. Therefore, logarithmic function never touch the y-axis. Therefore, logarithmic function never have y-intercept. Therefore, logarithm 0 is undefined. Okay, entonces, what is the conclusion? The conclusion is domain for the logarithmic function, que es the blue curve, is only from 0 to positive infinity. The negative part, no, pero don't touch 0. O sea, paréntesis, 0, infinity. This is the domain of logarithmic function. The range, no, because the range is the projection onto the y-axis. I can see is sometimes the logarithm have, the answer for the logarithm have positive number, like a 2, like a 1, 0, and negative 1, negative 2, negative 3, negative 4. The positive and negative, both, all real number. The answer for the range and the logarithmic function is all real number. Let me switch into the whiteboard again to write this idea that is important. Whiteboard, okay, waiting for me. Whiteboard switching. Wow, good. Okay, do you see whiteboard, right? Domain is for the logarithmic function.
No, I can't see the whiteboard.
No, okay, let me try again. Now? Now?
Yes.
Eso. Okay, good. Entonces, the domain is from 0 to infinity. No include 0 because logarithm of any base, I don't care, we have no restriction with the base of 0 is totally undefined. We study in detail when you're using the calculator, you put logarithm 0, regardless of the base, si es 10, si es undefined, error. Also, logarithm of any base of negative number, negative 1, negative 5, whatever, is also undefined. Impossible. However, the range, no, the range is all real number. And this is no surprise, because I suppose that you remember for the exponential function, wow, the television turned on alone. Okay, domain and the exponential function is a real number, because the exponential function is nice, but the range no. the range is from 0 to infinity. Only positive number in the exponential function. Y equal ax. But in the logarithm of y equal log a of x is completely opposite, because you remember in the inverse function interchange x and y. The domain of the exponential is now the range of the logarithmic, and the domain of the logarithm is now the range of the exponential. It's no surprise because it's the inverse function, no? One more important thing when 1, 2, 3. 1, 2, 3. 3 is x and z is the point when the logarithmic function crosses the x-axis, is the famous 1, 0. Wow, always, regardless the base, is the universal point in the logarithmic. And the y-intercept is known, because remember the logarithmic curve is asymptotically to the y-axis. Never touch. This is number 3. We always study together the x and y intercept, no? And number 4 is if the base is greater than 1, then the logarithmic function, the logarithmic function, because we are talking about logarithmic function, no? Is increasing. If the base is in between 0 and 1, suppose fraction, suppose logarithm base 1/2, the function is decreasing. I want to see now in this when the base is 1/2 or 1/3, you know, it's in between 1 and 0. And the most important point to plot by hand, not decimals. The logarithmic function is typical point. We study always. The first one is the universe, 1, 0. You plot that. Okay, the second question in the test 4 is, do the graph of the one arbitrary logarithmic function. The first question is, do the graph of exponential. Suppose 3 to the x. The second question is, do the graph of the one logarithm base 3 of x, or 5, or 4, or 1/2, or 1/3. Okay, never negative, never 1. And the typical point you plot is 1, 0 is universal, always. And the other is a, 1. Oh, yeah, because I know the logarithm base a of a is 1. Therefore, x is a and y is 1. And another point is logarithm base a of 1 over a is -1. Also, another typical point is 1 over a, -1. And also, don't forget the sixth property of the logarithm is number 6 property is if we have a vertical asymptote. And remember, the asymptote is important part of any graph. The curve, the function que contain asymptote, you need to do that. Okay, entonces es important. Look, this is suppose que I want to do the logarithmic function. Entonces you are doing a test something like that. Okay, and this point famous is 1, 0. And don't forget to do the graph of the vertical line. This is part of the important part of the graph. Okay, vertical asymptote at x equals. Okay, let's do it by hand now. So we have 6 property. Let me summarize quickly. Domain, only positive, not including 0. Range or real number. x-intercept 1,0, universal point. Y-intercept, no, we have no. When the base is greater than 1, increasing. When the base is in between 0 and 1, decreasing. Typical point 1,0, 8,1, and 1/2, -1. And don't forget the vertical asymptote. Okay? Okay, suppose in the test, I ask you do the graph of this logarithmic. Okay, this is just one elementary example. Suppose do the graph this function. F of x is equal logarithm base 3 of x. Okay, by hand, no decimal. When I plot my famous universal point, que I know is 1,0. I plot that. Boom. 1,0. But another famous point using the same number, que the base is 3. 3,1. Because I know que logaritmo base 3 of 3 es 1, ¿no? Ajá, entonces es 3,1. 2, 1 en y value. Pam, 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 pam. This point is this point. 3,1. And we're using another typical, it's 1/3. So I'm using the same family, no? The base is 3, so I'm using 1/3. It's a reciprocal, it's common negative. The 1/3, I suppose, using my imagination, is you take that segment in between 0 and 1 and divide by 3. The first division is 1/3. 1/3 -1 is here. This point is like that. This point is the point, 1/3, -1. And I connecting these 3 points like that. I know that I cannot forget the professor say that any logarithmic function contain one vertical asymptote at x equals 0. It's like that. Exactly on the y-axis. Vertical asymptote at x equals 0. It represents. That's it. This is the graphic I want by hand. Of course. The people who believe it's much better using the decimal, okay, you can use the decimal. Okay, let me try to spend the rest of the time to visualize what happens when the base is not 3, is a number less than 1. How change the shape of the logarithmic? I come back to decimals. And after, if we have time, we are doing by hand also, no? But let's do it in decimals now. Okay, I switch into decimals. Okay. Switching. Decimals. Okay. Decimals. Super. Okay, do you see decimal, right? Okay, this was the last example. I want to propose you another example. Look, this no anymore, close. This no anymore, close. Example 2. Example 2 is, wow, is when the base is 1/2. This is classical exponential decay. And the universal point 0,1. Remember the base is 1/2. Entonces, when the exponent is 1 is 0.5 in decimal, no? When the exponent is 2 is 1/4, 0.25. When the exponent is 3 is 0.125, que es 1/8. Entonces en -1 is 2 because it's a reciprocal. What is the reciprocal? See, your exponent is -1. Your reciprocal is 2/1, que es just 2. And when the exponent is -2, it's reciprocal and square. Flip it, it's 2, square is 4. Okay, this is the exponential. You know very well. Don't make a real number. And the range is only from 0 to infinity positive, no including 0. Okay, understand very well. But let's see now the contraparte of the opposite situation for the logarithmic. Logarithmic when the base now is 1/2. What the hell? Look at that. Now the base is 0.5. Look, 0.5. Okay, 1/2. 1/2. Again, we have the same situation. A symmetric let me change the color. Logarithm blue. Logarithm blue. Look blue. Exponential red. Okay, this is the exponential is decay, is decreasing, and the logarithm is also decreasing. But look, this famous point is 0.1 in the exponential universal now is 1.0 in the logarithmic. This point is 1.0.5 in the exponential, and now in the logarithm is 0.5,1. Remember, you interchange x and y. And the property is the same. Domain is the same regardless que es base greater than 1 or less than 1, it's the same. And range is the same. The only property que change is que es decreasing. The function is decreasing when the base is fraction. Okay, it's the only thing it change. The base is decreasing. Let me switch to the board. Whiteboard. Whiteboard now. Okay. Let me try to spend time now to, for example, supposing the test, I am bad guy. I do the graph of this exponential function. Look, the logarithmic function, sorry. F of x is equal logarithm base 1/3, whatever, of x. Do the graph. Entonces, immediately I saw, wow, the professor explained me when the base is a fraction, it's decreasing. Okay, no problem. Plus point get the universe, 0.1. 0.1, no, 1.0. And the exponential is 0.1, but and the logarithm is 1.0 because I know the logarithm of 1 is 0. I plot that exactly the same. Look, it doesn't matter if the base was 3 or the base was 1/3, passing through the same point is 1.0. Okay, now I select another point. Of course, I select the point as a family 1/3, so 3, 9. Entonces, suppose 1/3, the answer is 1, no? Because logarithm of 1/3, when the argument is 1/3, es obvio que es 1, no? Entonces, 1/3, 1, 1/3 is here, 1 is here. It's a 1, this is a negative 1, 1/3. That point is the point, that point. 1/3, 1. And 3 is, I have no idea. You put 3 here, logarithm base 1/3 of 3. Oh, it's the same, pero flip it, reciprocal. Entonces, el reciprocal es negative 1. Entonces, 3, que es here, 1, 2, 3, es negative 1. That point is this point, negative 1. Okay, I do the graph using the blue color, connecting this point, and this point. I can see again that this graph is decreasing, and I cannot forget the vertical asymptote on the y-axis. X equals 0, vertical asymptote. Any question, guys? Any question? So now, third day, everyone bring your calculator because we are working with the calculator. Okay, everyone bring your own calculator. Third day because we are studying how we compute the logarithm using the calculator. Okay, guys, I love you so much.